So today it's our great pleasure to have Naci Saldi joining from Bilkent University. And so Naci is going to talk about learning in discounted cost and average cost midfield games. So thank you very much, Naci, for accepting the invitation, and the floor is yours.
Okay, yeah. Thank you for the invitation and introduction. So as you said, today I'll be talking about learning in discounted cost and average cost midfield games. And this is a joint work with my colleagues Berkay Anahtarcı and Can Deha Karıksız. So they are working at Özyeğin University in Istanbul. So I was there until last semester, and this semester I started working at Bilkent University Department of Mathematics. And this is the outline of my talk. I will first give the formulation of mean field games, both for finite agent setting and then for infinite agent setting. And then I will define the mean field equilibrium. After this, I will talk about computation of mean field equilibrium when the model is known. And finally, I will be interested in learning mean field equilibrium when we don't have the model. Okay. So this is the setup in finite agents setting. So we have L computing agents, and each agent has the following state dynamics. So P is the transition probability of agent I, and this transition probability is identical for each agent. And it gives the next state distribution given the current state action information as well as the mean field term. So this dynamics is very similar to the dynamics we have in Markov decision processes, but we have this additional mean field term, which is indeed the empirical distribution of the states of agents. Therefore, agents are coupled through their dynamics because of this term. Okay, and each agent generates its action using a policy. Okay, and this policy is indeed a sequence of functions, and for each time, this function maps the current state information of the agent to its action space. Therefore, agents are allowed to use only their local state information. Okay, so they cannot observe or use the global state information. And for a given joint policy, the cost of agent I can be a discounted cost, which has this form, or the average cost in the stock. So here beta is the discount factor. Here in the expectation we have function C, and this function is called one-stage cost function. Normally in Markov decision theory, this cost function depends on the state information and the action information. However, in mean field games, the mean field term also affects this one-stage cost function. Therefore, agents are also coupled through their cost functions. Okay? And since our agents are coupled through their dynamics and cost functions, this is a game problem, and therefore the standard notion of optimality is the Nash equilibrium. Okay? And here's the definition of Nash equilibrium. So a joint policy is a Nash equilibrium if we have the following identity for each agent I, and it says the following: at the equilibrium policy for agent I, the policy in the equilibrium is the optimal one given the policies of other agents at equilibrium. Okay, so this is a classical definition in game theory. However, in mean field games, there are two challenges pertaining to Nash equilibria. The first challenge is the decentralized nature of the information structure. So we assume that agents can only observe their local state information. They cannot observe the global state information. And because of that, the problem is indeed, or the information structure of the problem is indeed a decentralized one. Okay. This is the first challenge, and the second challenge is the curse of dimensionality. So the solution of the problem becomes intractable when the number of agents or states actions are large. Okay, and therefore it is of interest to find an approximate decentralized equilibrium with reduced complexity, and this is where the mean field game approach comes in hand. Okay, and in mean field approach, actually instead of computing or obtaining an exact Nash equilibrium, we are interested to compute or learn epsilon Nash equilibrium or approximate Nash equilibrium, and this is the definition of epsilon Nash equilibrium. So a joint policy pi star is an epsilon Nash equilibrium, where epsilon is a very, in general, is a very small number. If we have the following inequality for each agent I, and this inequality says the following: at the equilibrium policy, the policy in the equilibrium for each agent is indeed epsilon optimal given the policies of other agents at the equilibrium. Okay, so here in epsilon Nash equilibrium, instead of optimality, we require the epsilon optimality of the policies in the equilibrium. So this is the definition of approximate Nash equilibria. And what we want to do, okay, by going to the infinite population limit, okay, we want to decouple agents from each other and obtain a classical Markov decision process and solve this problem, and then go back to the original finite agent setting and prove that the policy, the equilibrium policy or the optimal policy in the infinite population limit is indeed an epsilon Nash equilibrium if we have a sufficiently large number of agents. Okay? So this is the main idea in mean field games. Okay? So therefore, I will next explain the infinite population formulation of mean field games. And before giving the formulation, let me motivate it. So suppose that each agent in the finite agent setting uses the same policy. If this is the case, then by symmetry, we can show that the mean field term at each time t converge to some deterministic distribution mu t, okay, as the number of agents converge to infinity. And this is by law of large numbers. And also this limiting distribution mu t is indeed equal to the distribution of the states of agents at time t. Okay? Therefore, since we have this result by law of large numbers, we can model the collective behavior of agents by a state measure flow mu, which contains these limiting deterministic distributions. Okay. And therefore, in the infinite population limit, the problem that we have is the following. We have a state measure flow which models the collective behavior of agents, and a generic agent is competing with this, okay, collective behavior. Okay. So it should act optimally against this state measure flow and finds the optimal policy. And when each agent applies this optimal policy in the infinite population limit, then the distribution, the state distribution of each agent should be consistent with the state measure flow. So this is the main idea in mean field games. And in this talk, we are only interested in stationary mean field games. Therefore, I assume that for all t, mu t is equal to mu. Okay. And this suggests the following definition as the infinite population limit of mean field games. Okay. So given a mean field term mu, which is the limiting distribution of mean field terms, a generic agent has this following state dynamics. So this state dynamics is exactly the same state dynamics that we had for the finite agent setting, but in place of the mean field term ETL, we have its limit mu. Okay, Therefore, given any mu, indeed, this is a state transition probability of a Markov homogeneous Markov decision process. And since we have a stationary problem or homogeneous Markov decision problems, we are only using stationary policies, okay, to optimize our cost function. Therefore, for any time t, we are using the same function pi, which is a mapping from the state space to action space. Okay, and the policy pi star is optimal for mean field term mu if it minimizes the corresponding cost function. This cost function is either discounted cost or average cost. And again, in the description of the cost function, you have to replace the mean field term with its limiting distribution mu. Okay. And what's the equilibrium notion and the infinite population limit? So to define the mean field equilibrium, I have to define the two set valued mapping. The first set valued mapping is this. So it maps the mean field term to the set of policies. And indeed, for any mu, it gives the set of optimal policies for mu. Okay. So this is the first set valued mapping. And the second set valued mapping is the following. So it maps any policy to the set of mean field terms, and it does the following: given any policy pi, this set is a set of invariant distributions of the state process under policy pi. Okay, so remember our state dynamics is homogeneous and our policy is stationary. Therefore, we can talk about the invariant distribution of the state process. And here's the definition of mean field equilibrium. A pair pi star mu star is a mean field equilibrium if pi star is the optimal policy for mu star and mu star is the invariant distribution of the state process under pi star. Okay. So this is the definition of mean field equilibrium. And our goal in this talk is to compute this mean field equilibrium when we know the model and to learn it when we don't know the model. Okay, so this is the main goal of this talk. By the way, can you hear me?
Yes.
Yes, we can hear you.
Okay. Okay, yeah. Thank you. Good. So let me continue. So if you have any questions, you can interrupt me anytime you want. Okay. So the objective of this talk is computing or learning this mean field equilibrium, and we will do this first for the discounted cost and then for the average cost. And indeed, the analysis in the average cost is very similar to the analysis in the discounted cost. Okay, so let me start with discounted cost. And here are the assumptions for discounted costs. So first of all, we are assuming that one stage cost and the transition probability are Lipschitz continuous. So remember, they are functions of state action and mean field terms. So I'm assuming that these functions are Lipschitz with respect to their inputs. And the second assumption is important. Given any state x, function v, and mean field term mu, this capital F is indeed a function of actions, okay, defined like that. And I'm assuming that for any x, v, and mu, this function is rho strongly convex. And moreover, its gradient with respect to actions, is Lipschitz continuous. Okay. And indeed, we need this assumption B for discounted cost to prove the Lipschitz continuity of the optimal policy with respect to mean field term. Okay. This is indeed the most important part in this presentation. So before describing the mean field equilibrium operator that gives the mean field equilibrium. Let me briefly talk about how we can compute the optimal policy, okay, for Markov decision processes. So remember, given any mean field term mu, the problem, okay, a generic agent is facing is indeed a Markov decision process, okay, because it has a homogeneous state transition probability. And given mu, the cost of policy pi with initial state x is defined like that, okay. And the cost function is the infimum or the minimum of this, okay, function j mu pi x over pi. And we know that the optimal value function is the unique fixed point of the beta contraction Bellman optimality operator. So this is the Bellman optimality operator. It's a beta contraction. Therefore, it has a unique fixed point, and this unique fixed point is our optimal value function. And if pi mu minimizes the right-hand side of the Bellman optimality equation, then it is the optimal policy for mu. Okay. So this is the one way. This is one way to characterize the optimal policy using the optimal value function and Bellman optimality equation. We can also characterize the optimal policy for mu using Q functions. So if I define the optimal Q function like that, okay. So as you can see here, I removed the minimization operation in the Bellman optimality operator equation, and it gives me the optimal Q function. But using Bellman optimality equation, I can also derive that the minimum of this Q function is indeed the optimal value function. Therefore, I can write first equation as a fixed point equation. Okay. So in the second equation here, this is indeed again a beta contraction operator on Q functions, and the fixed point of this beta contraction operator is our optimal Q function. And what is the optimal policy in this case? The optimal policy, pi mu, is the function that minimizes this Q function. Okay. So therefore, this is another characterization of the optimal policy. And actually, since the operator applied, the optimality operator applied on Q functions as beta contraction by using Banach fixed point theorem, we can easily obtain an algorithm that gives this optimal Q function. So by iteratively applying this optimality operator, we can actually obtain this optimal Q function, and from this optimal Q function, we can compute the optimal policy. And now it's time to define the mean field equilibrium operator. So our mean field equilibrium operator is denoted by H, and it is a mapping from mean field terms to mean field terms, okay? The set of mean field terms to set of mean field terms. And it's a composition of two operators. The first operator is H1. So given any mu, it gives the optimal Q function for this mean field term mu, okay? So actually we can compute the optimal Q function given any mean field term using the optimality operator that we have over here, okay? And our second mapping is H2, and it does the following. Given any mean field term and Q function, it computes the new mean field term using this, okay, equation. So here, pi q depends on the Q function that we have at the input, and it is indeed the policy that minimizes this Q function. Okay? And this is our second operator, and if we compose these two operators, H1 and H2, we obtain the mean field equilibrium operator. Okay? So it has the following description. Given any mu, we first compute the optimal Q function, and then using mu and this optimal Q function, we generate our new mean field term. And here's the first theorem, and indeed this theorem leads to the value iteration algorithm for computing mean field equilibrium. So is there any question?
So sorry, I see one quick question on the previous slide. So when you
Yes.
define the optimal policy, you take the
Yes.
argmin. I don't remember,
Yes.
did you assume that there is a unique argmin, or there could be multiple optimal actions?
Oh, I see. Yeah. Okay. Actually, because of the second here assumption, I'm assuming that the Q functions are strongly convex in action variable. Therefore,
I
there's a
see. So
unique optimal policy. Okay.
okay, makes sense. Yes,
So the
okay,
function
thank you.
space that Q function lives in has some structure, strong convexity and other structure. Okay, because of this second assumption. Therefore, there's a unique optimal policy. Okay.
I see. So somehow you make this assumption not explicitly on the Q function directly, but the fixed point. So basically,
Actually, I'm
the fixed point of the
defining.
Bellman equation.
Yeah, exactly. But since we have this assumption here, the fixed point of this Bellman optimality equation should satisfy some convexity and other conditions. And because of that, we have
I
actually
see.
a unique minimizer for any Q function. Okay.
Yes, and this condition is, can you check it easily, or the condition 2 that you have, yeah, right,
This
B
one,
here, condition, because you don't know the Q function in advance, right? So how do you know if the Q function is going to satisfy, is
I
going to
don't
be
know.
roast?
Yeah,
Okay.
I think it shouldn't be difficult. For instance, if our one stage cost function is quadratic in A, and if P has some density with some convexity condition, you can easily check this probably. Yeah.
Okay.
I think
Okay,
it's
thank
not
you. And so
difficult to
thanks
check.
to that, okay, yeah. And then you have convexity of the Q function, and then you have strict convexity,
Yeah,
and so then
exactly.
you
Yeah,
have
exactly. So we have the
uniqueness.
same actually conditions that we have here in assumption B. So it is strongly convex, and we can also put this assumption, this smoothness assumption on this gradient. Okay.
Okay, thank you.
Yeah. Good. So let me continue. So good. So this part is important. H is contraction, and actually from here we can derive our value iteration algorithm, and this is also very important to establish the error analysis in our learning algorithm. Okay, and since this is important, I want to give the sketch of the proof of this fact. Okay, so first of all, using classical techniques, we can easily prove that H1 is Lipschitz continuous with Lipschitz coefficient KH1. Okay. This part is not difficult, but the second part is the important part here. So given any mu and mu hat, pi mu and pi mu hat are the corresponding optimal policies. Therefore, pi mu x is the unique minimizer of this function. Okay, so if you recall the definition of capital F, pi mu x is the unique minimizer of this capital F with the inputs. And similarly, pi mu hat y as the unique minimizer of this function capital F with the following inputs. Okay. And we assume that capital F is strongly convex. Therefore, by using strong convexity of F and also the first order optimality condition for convex functions, we can prove the following inequality. Okay. So the gradient of F with these inputs, inner times dot product, the difference between the policy and or equal to rho times the L2 distance of the difference between policies. Okay. This is our first inequality, and this comes from strong convexity of F, and using the smoothness of F or the Lipschitz continuity of the gradient of F, we can also obtain an upper bound to the same quantity like that. So here Kf is the Lipschitz constant of the gradient of F, and we have again the distance between policies and these. the term in the parentheses. So here we have the distance between x and y. We have the distance between optimal Q functions, and we have the L1 distance between mu and mu hat. Okay. But here in this inequality, we have the first power of the distance between policies, but in this inequality, we have the second power. Okay. And we know that the L infinity distance between Q functions is indeed equal to the L infinity distance between H1 mu and H1 mu hat. Okay, so this is by definition, and we proved that H1 is Lipschitz, therefore this is less than KH1 times L1 distance between mu and mu hat. And from here, and by using these two inequalities, we can easily derive the following inequality. Okay. And this inequality indeed implies that optimal policies are Lipschitz continuous with respect to state as well as the mean field term. And this is indeed the most important part here. Normally in Markov decision theory, we don't require this. In general, in Markov decision theory, in general, we prove that the optimal value function or the Q function is Lipschitz continuous. It is not necessary to prove that the optimal policy is Lipschitz continuous, but in this case, since the optimal policy affects the new mean field term through our state dynamics, and if we want to prove that this operator is contraction, then we have to establish that this optimal policy for any mu is Lipschitz continuous with the state and as well as the mean field term. Okay, so this is the most important part here. And using this fact, classical techniques, it is straightforward to prove that our mean field equilibrium operator is contraction. And of course, here we also put some conditions on the Lipschitz coefficients here. Okay, so we put some smallest conditions on the Lipschitz coefficients of C, P, and the gradient of F, as well as some condition on the coefficient rho. Okay, so that this operator becomes contraction. Good. Since our mean field equilibrium operator is contraction by Banach fixed point theorem, the following algorithm gives the fixed point mu star of H, and also using mu star we can compute the corresponding optimal value Q function. Okay, so this is the algorithm, and why this mu star and the optimal Q function is important are important because if we have mu star and Q mu star, where mu star is the fixed point of our mean field equilibrium operator, then mu star, pi mu star, where pi mu star is the optimal policy for this Q function, is indeed a mean field equilibrium. So you can actually easily prove this by using the definitions of the operators H1 and H2. And that's why this algorithm is important. Okay, so by iteratively applying H to mean field terms, we can obtain mu star, and using mu star, we can obtain optimal Q function. And from there, we can extract the optimal policy for mu star. And since mu star is a fixed point of H, we can prove that this pair mu star pi mu star is a mean field equilibrium. Okay? So this is the value iteration algorithm, and this works when we know the model. So do you have a question?
Yes, sorry for the interruption. I have one more quick question.
Fine.
So here, this one is value iteration in the sense that, so what is the connection with the classical value iteration algorithm? Is it that when you get rid of the mean field term, you recover?
Yeah, actually,
let's imagine there is.
So we call it value iteration, but it's not exactly value iteration. So here, at this step, we are actually doing a value iteration. For any given mu, we are applying the value iteration algorithm. Okay. But here we are not probably.
So if we take
Not
a
a
mean field
good
game,
terminology. Sorry.
oh yes, so I would have thought that maybe if we take a mean field game in which there is no mean field interaction, so basically each player is solving an optimal control problem independently,
Yes, exactly.
then it converges in like one iteration, I guess. And this iteration amounts to do value iteration, or is it?
Yeah, probably
something like
something like that. So if we don't have this mean field term, then or the mean field term is fixed, then this is indeed a value iteration algorithm, this step. Okay. But
I see. So basically, the operator H1 is computing the optimal Q value, and that's why you call it value iteration.
Using value
Okay.
iteration algorithm, yeah. But maybe it's not a good terminology. Maybe
No. I'm just
it's better
asking
to change
to understand. Yeah, it makes sense. Yeah, thank you.
Yeah.
Yeah, I have another question.
I think there is one more question. Yeah.
Yeah. Sure.
So, given the assumption you do, you ensured that there's a deterministic policy that will correspond to the Nash equilibrium, right?
With our yeah, okay, yeah, we can prove that there exists a deterministic policy in the mean field equilibrium. The policy in the mean field equilibrium is deterministic. Yeah, can be proved. Is this your question?
Yeah, it was my question, and the follow-up is, but maybe we can discuss this later. What kind of problems can be modeled by this kind of things? I mean, I'm more used to, say, finite horizon things and Cron modeling things. So in this case, you want to have something which is stochastic in general. So, or another way to see this is if you remove the dynamics, not the dependency of the dynamics to the population, but you just remove the dynamics such that you have a static game, an infinite static game. What class of games would be covered by this kind of Lipschitz-net assumption that ensures the contraction of the operator you're working with?
So, actually, I couldn't hear your last sentence.
So if you remove the dynamic, so that you have a single state, no dynamics.
Yes.
And so you get with a static mean field game somehow. And how have you thought about what kind of games would be encompassed by your framework?
Oh, I see. So in this case, we don't have, in this assumption, the second term, just the cost function, right?
Yeah.
Oh, I see. Yeah. In this case, so this cost function, let me see, should satisfy these conditions, I guess. So, okay.
So in this case,
actually, I'm not
like for
sure.
every fixed.
Yeah, I'm not sure. Yeah, for static case, I don't actually know how we can do similar analysis. Yeah, actually, I don't know for static case, so I have to think about it.
Okay, but I don't want to stop.
Okay, yeah. I don't know for the static case. I have to think about it. Yeah, I'm not sure about that. I'm not sure if we can do this under these assumptions. I'm not sure. Okay.
Okay. Thanks.
Yeah. So, okay, yeah, good. So this is the algorithm that we have when we have the model. If we don't have the model, then we have to develop a learning algorithm. In our mean field equilibrium operator H, we have two parts, H1 and H2. Okay, given any mean field term mu, H1 computes the optimal Q function, and H2 computes the mean field term using the current mean field term and the corresponding optimal Q function. Therefore, in the learning algorithm, by doing some simulations, we will replace these H1 and H2 with random operators H1 hat and H2 hat. Okay, so this is the main idea, and this is the description of the random operator H1 hat. So here, H1 basically compute the optimal Q function given any mean field term. Therefore, at this stage, we can apply classical learning algorithms in Markov decision theory. And actually, I forgot to tell you this. In this talk, we are assuming that our state space is finite and our action space is an uncountable convex compact subset of an Euclidean space. So therefore, our action space is not finite, so we cannot apply classical Q-learning algorithm here. But instead of this, we can apply fitted Q-learning algorithm, and this is a description of fitted Q-learning algorithm. So here, N is the number of data points, L is the number of iteration, and M mu as the input, the mean field term. And our goal is to compute the corresponding Q function. So how can we do this using fitted Q-learning? We first generate IID samples of state and action, okay, using some distribution, and this distribution satisfies some mild conditions. Okay, and then using these samples, we first obtain the corresponding cost function, and then we simulate our dynamics at these state action pairs. Okay, and we get a new state variable one. And then using these data points for each iteration, we form this empirical risk. Okay, and then we find the function little f that lives in this function class. So this capital F is some fixed function class. For instance, it can be the collection of neural networks with some specific architecture. It can be a linear span of finite number of basis functions. Okay, so from this function class, we pick the one that minimizes this empirical risk. Okay, and the minimum becomes the new Q function in each iteration, and we do this L times, and at the output we will obtain some Q function. Okay, so this is the fitted Q-learning algorithm, and here's the error analysis of the Q-learning algorithm. If we pick N and L large enough, then the distance L, infinity distance between H1 hat and H1 is very small. Here, delta is the representation error due to the function class F, capital F. In general, we don't know if our Q function lives in this function class, but we'll believe that it is large enough so that we can approximate our Q functions very well using the functions from this function class. So in general, we can take this representation error delta very small. Okay, so this is the error analysis, and this is the random operator H2 hat that replaces H2 in our algorithm. So remember, H2 computes the new mean field term using our transition probability, okay, given the current mean field term and the Q function. Therefore, we need the simulation or the estimation for our transition probability P for at each state. And since we have finite many states, we can actually obtain this estimate or empirical estimate for our transition probability at each state using a simulation. So if you do a simulation at each state for your transition probability, and if you take the empirical distribution of the data after the simulation, then it is your empirical estimate for your transition probability. And using this empirical estimate, you can actually compute the new mean field term approximately like that. And this is their analysis. If you, by using Hawking's inequality, it is very simple to prove this. So the L1 distance between H2 hat and H2 is very small if you pick M large enough. Okay. And if you combine these two error analysis, you can actually. So first of all, before the error analysis, let me give the overall learning algorithm. Okay. So here in the overall learning algorithm, we replace our mean field equilibrium operator H with the random operator H hat, and the random operator H hat does the following. So at each iteration, this is very similar to H. Okay. First, by using H1 hat, we are computing approximately the optimum Q function, and then using this approximate Q function and the mean field term, we approximately compute, okay, the mean field term using H2 hat. Okay, and we do this k times, and at the output we obtain some mean field term mu k, and then using this mu k and using H1 hat, we generate our approximate Q function for mu k. Okay. And using the error analysis for H1 hat and H2 hat, we can obtain the following result. And it basically says the following: if you pick the parameters in H1 hat and H2 hat large enough, then suppose mu k and qk is the output, are the outputs of the learning algorithm H hat. Okay, and define pi k as the minimizer of the Q function qk, then the distance between pi k and pi star, where pi star is the equilibrium policy in mean field equilibrium, is very small. So here, this k epsilon delta is a function which goes to 0 as epsilon goes to 0. Again, we are assuming in general that this delta representation error is very small. Okay, so this is the first main result for discounted cost. Therefore, the learned policy is very close to the policy in the mean field equilibrium. And why this is useful? This is useful because of the following result. So in general, we know that pi star, the policy in mean field equilibrium, when is applied to the finite agent setting, gives the approximate Nash equilibrium, and the same is true for pi k. So if each agent applies pi k, okay, in the finite agent setting, then the joint policy is approximate Nash equilibrium. Okay. So this is our second main result for discounted cost. So how many minutes do I have, Matthew?
I guess we started late, so I think you still have 15 minutes or something, 10-15 minutes.
Okay. Yeah, 15 minutes should be enough. Okay. Thank you.
Sure.
So this is what. Okay, good. So this is what we have for discounted cost. So let me continue with average cost. Actually, the analysis and the ideas are very similar with the discounted cost. Okay, there are some different parts in the analysis. Let me explain these differences shortly without going into the details. So first of all, these are the assumptions that we have for average cost. They are almost the same with the assumptions that we have for discounted cost, but we have additional assumption on the transition probability. So we are assuming that there's a sub-probability measure lambda on state space X such that our transition probability is lower bounded by this sub-probability measure. So the sub-probability measure is called minorizing sub-probability measure, and it is used a lot in the analysis of average cost problems in Markov decision theory. Okay? And the other assumptions are very similar, and the only difference is the following: in the description of capital F, we don't have beta term anymore. Okay. And again, before I will describe our mean field equilibrium operator, let me explain to you how we can compute the optimal policy for any mean field term mu. Again, we define a Q function, which is a fixed point of the following operator. So here, instead of our transition probability P, in the definition of this operator, we have little q, where little q is defined as the difference between our transition probability and the minorizing subprobability measure. Okay. And if I define this operator like that, then I can prove that it is indeed a contraction. Okay. And the fixed point of this contraction operator is defined to be this Q function, Q mu star. And why this Q function is important or useful? Because the policy pi mu that minimizes this Q function is indeed the optimal policy for our average cost problem given any mu. Okay, so this is how you can characterize the optimal policy in average cost problems if you have this minorization condition. Okay, good. And since this operator is contraction, by iteratively applying this operator to Q functions, you can eventually obtain the Q mu star for any mu. Okay, and the definition of mean field equilibrium operator is the same. So H1 gives the optimal Q function for any mean field term, and H2 gives the mean field term given the current mean field term and the Q function, and the composition of these two operators gives the mean field equilibrium operator. Okay? And again, we can prove that it's a contraction. Therefore, we can actually construct the following value iteration algorithm. This is the same value iteration algorithm that we had in discounted cost. Questions?
Yeah, sorry, one quick question on the previous slide. So when you say it is the same, you mean, okay, at a high level it is the same thing, but I guess,
exactly.
So the difference would be in the definition of Q in H1. The Q is not the same.
Exactly. So when you are computing the Q function, you are actually applying a different operator.
Okay, makes sense.
So in discounted cost, we have our transition probability here and beta in front of the summation, but in average cost, we don't have beta term, but instead of our transition probability, we have this sub-transition probability Q. Okay, this is the difference.
Okay. Thank you.
Good. So we have this value iteration algorithm, and at the output we have mu star and the Q function corresponding to the mu star, and the minimizer of the Q function is denoted by pi mu star, and this pair is indeed the mean field equilibrium. Okay, again, you can prove this by using this analysis here. Good. And again, if you don't know the model, we have to develop a learning algorithm. So we have to replace H1 and H2 with random operators, the same thing that we did in discounted cost. And this is the fitted Q learning algorithm for average cost. So as you can see here, we don't have beta term in the description of the empirical risk. And the problem we have in average cost is the following. In the description of this operator, instead of transition probability, we have this sub-transition probability Q, okay? And therefore, normally when we are generating our data, we need to use this Q sub-probability measure instead of, sorry, Q sub-transition probability measure instead of P, okay? In general, we need to do this. However, unfortunately, we don't have access to the sub-probability measure lambda, so we cannot use lambda to generate data. So because of instead of that, we have to use our transition probability to generate data. And because of this, when we are doing the error analysis of the fitted Q-learning algorithm here, we have to work with span seminorm instead of L infinity norm, okay? Because if instead of Q, if you have P here, instead of Q, if you have P here, then this operator is no longer a contraction operator with respect to suit norm. But what you can prove that this operator is indeed contraction with respect to span seminorm. And that's why, and since we are generating our data using our transition probability, not sub-transition probability Q, we have to work with span seminorm. And if you work with span seminorm, you can actually prove a very similar result. Okay, and it says the following. So the span seminorm between H1 hat and H1 is very small if you pick N and L large enough. Okay, again, we have delta, which is the representation error, and we assume that this, or at least we expect that this is very small. And here is the definition of span seminorm. The span seminorm of any function is the difference between its maximum value and the minimum value. And we have this inequality. So it's always less than 2 times. Of course, this should be F, not G. Okay. Good. So this is the error analysis of the fitted Q-learning algorithm, but this is fine. So instead of infinity norm, it's enough to have error analysis in terms of span seminorm, because what we are interested in, the minimizers of policies. So minimizers of these Q functions, okay? So we are interested in the minimizers of these Q functions. And if the span seminorm of 2 Q function is small, then the distance between their minimizers are also small. So you can prove this, okay? And the description of the random operator H2 hat is the same as the H2 hat that we have for discounted cost. The same error analysis, and this is the overall learning algorithm. Again, same with the discounted cost. Of course, here H1, the operator in the fitted Q-learning algorithm is different than H1 hat discounted cost case. And this is the first mean result for the average cost. Again, suppose mu k, qk is the output of the learning algorithm, and if pi k is the minimizer of the Q function qk, then the distance between pi k and pi star is very small. Again, pi star is the policy in the near field equilibrium. This is the first mean result, and the second mean result is the following. If each agent uses pi k, then if we have sufficiently many agents, the resulting joint policy is approximately Nash equilibrium. Okay. Good. So this is what we have about average cost, and I think this is the end of my talk. So thank you for your attention. So if you have any questions, I'm glad to answer. Okay.
Great. Thank you very much.
Good.
It was very clear, but maybe there are some questions.
Yeah. You can see my slides, right?
Yes, we can still see your slides. Yes.
Okay, yeah, perfect.
Yes, I think there is a question.
Hi. Hi. So thank you for the talk, Naji. It was really nice. So I had a question about the H2 hat operator.
Yes.
I was wondering, can you have like, so I think you take IID samples from
Exactly, yes.
generator. Okay. So how difficult would it be to have like some sort of to approximate this quantity by like a Markov chain? So if you have like a Markov chain and you're like kind of reading samples from it instead of the samples being IID, would that be very hard to approximate this quantity?
Oh, I see. Okay, I see. No, yeah, let me. So
basically, I think IID, the IID
okay,
assumption, if how can we relax that? I guess that's what I'm trying to.
I think if this Markov chain satisfies some ergodicity condition, you can do that. Yeah.
Right. Right. Okay. Yeah.
You can do that if the invariant distribution of this Markov chain corresponds to the transition probability at a specific state, then if this Markov chain has some ergodicity property, then you can actually prove it.
Right. Right. Okay.
And if this Markov chain is geometrically ergodic, then you can indeed obtain some
right.
error analysis as well. Yes.
That
I think
makes
you
sense.
can do that. Yeah.
Thank you.
So related to that, actually, what you estimate here is really the next distribution, right? It's like you start from mu, let's say,
Yeah,
and you
next
want
mean
to
filter.
estimate. Okay, but it could be different from the stationary distribution, right? If you start from mu and you apply repeatedly the policy, maybe it will converge to some stationary distribution that is different from just the next one, right? Except if mu is already stationary.
Yeah, exactly. Yes, exactly. So this is another way to do that. Yeah. For instance, in the algorithm, what you can do, you can apply this transition probability several times, and then maybe you can converge to the invariant distribution corresponding to your policy pi. Okay. So you can also do this.
Makes sense. Sounds good. Yeah. Thank you. More questions? Yeah, Mathieu.
Yeah, thanks again for the talk. It was very interesting. I'm wondering, you have this H operator, even without approximation, where you evolve for one step the population, then you solve for best response. And my question would be, even with the exact model, assume that instead of computing the best response, you compute a kind of greedy policy for the current policy. You do a kind of optimistic, you improve the policy, but you don't compute the best one. Or instead of evolving the population for one step, you evolve it for multi-step, because you're somehow doing simulations, say, and maybe you cannot afford to compute the best response in only one step, the evolution of the population. How will, I guess the analysis will not hold as is, but could the approach be adapted to this kind of setting?
Yeah, I think what you can do, instead of using optimal policies, you can use the Boltzmann policies, right? So instead of minimizing the Q function, and then you, at each step, you can gradually decrease the inverse temperature or the temperature, I don't know.
You would decrease the temperature.
Yeah, you can do this, and probably you can prove similar results by doing this. Is this your question?
It was more because if you take the Boltzmann policy, we take the Boltzmann policy according to Q star, the optimal Q function, so you still have to solve an MDP. But imagine that you want to solve an MDP in the infinite horizon setting, and you do a policy iteration. So policy iteration is it will be a finite number of time steps.
Okay, I see.
But instead of doing the full policy,
yeah, I see.
You do just one step.
Just once. Okay, I see.
So you get some improvement. It's better.
Yes,
but it's not the best possible policy.
So you are saying something like policy iteration, right? Okay, I see. Okay. I'm not sure. I'm not sure. I have to think about it. But if we apply this operator, okay. I'm not sure. I have to think about it. Maybe we need to apply several times this optimality operator so that we have some bound on the difference between optimal Q function and the Q function that we have. So, but I'm not sure if it is enough to apply once this optimality operator and then continue like that. I have to check.
What I'm pretty sure of is that if your improvement is too small, you can make process converge to something which is suboptimal. If the improvement is too small, if the improvement is the optimal policy, it will work. But yeah, it's probably a quite open question. But if you're in between, you want to be in between because you generally don't want to solve reinforcement learning as a third problem of something bigger. You want to interleave all learning aspects. I mean, to do kind of practical algorithm with deep learning and so on, whereas the theory no longer hard. But so the question is somehow what kind of minimal improvement do we need to have this kind of convergence?
I see.
And so it's probably quite open.
So maybe instead of this value updates, we can use policy iteration there, maybe. So we can, apply this the IDM policy iteration, so we know that it improves the cost function, and then we can continue like that. Maybe, but I'm not sure.
Sorry, but sorry to interrupt, but since he had the assumption of strong convexity in the cost, and he said that this transfers to the Q functions, then it's going to improve fast, more or less. I mean, okay, if we drop the convexity, then this is a different story, but the convexity is going to go fast, no?
Yeah. So maybe.
With the strict convexity. This is going to be a problem.
I have to check the proofs. So the thing is, the optimal Q function satisfies this fixed point equation, right? Probably in the proofs we are using this fixed point idea, but if we can avoid this fixed point equation in the proofs, then we can do that. So by applying once the optimality equation, we obtain some Q function, and then using this Q function and mean field term, we generate our new mean field term, and we can continue like that. It's very similar to the value iteration in Markov decision process. Yeah, I have to check the proofs, but I don't know at this point.
It would change the very definition of the operator that you.
Yeah, exactly. And in this case, in the learning algorithm, what we can do, we can again simulate the transition probability, and instead of applying Q learning, we can simulate the transition probability and then apply the optimality operator using this simulated transition probability. No need to apply Q learning algorithm. Okay. So if this works, but I have to check that.
Okay, thank you. More questions or? Okay. Well, thank you very much, Naci, again for the very
Yeah,
nice talk,
thank you, Matthew.
and
Thank you
thank
for
you
the
everyone.
invitation and nice questions.